So we shall start now. Okay, fine. So welcome to the course. The main course we are about to learn is about sorry, yes, universe. Okay, you are getting my noise. Oh, sorry, my voice clearly. I suppose everyone is fine. So
Yes.
okay, so take this word relativistic. What does it broadly mean? It's Einstein's general theory of relativity. Okay, and we take this universe, and it can be said that in four dimensions. Okay, four-dimensional space. Okay, which can be further split into 1 plus 3 dimensions, where this one represents our time and this three represents our spatial dimensions. Okay, and that's why this is my whole four-dimensional space-time. Okay, it can be called a four-dimensional space-time. So we're gonna start to know what is the relativity and what is the how relativity works in our universe, and what is this word relativistic universe means, that we are applying the Einstein's general theory of relativity onto a four-dimensional space, that is actually three-dimensional, three spatial dimensions and one time dimension. We combinedly call it the four-dimensional space-time. At the level of this course, we are just considering three dimensions of three spatial dimensions. Okay, at the level of this course, no any further dimensions we are taking. So for other students who will be watching my videos, let me introduce myself. Okay, I am Raghav Kumawat. Okay, pursuing my integrated PhD from ICER. Sorry about my handwriting. I'm just about beginning this thing, new device, writing pad. Yeah, in physics. Okay, so basically, it's my third third year. Okay, so it's integrated PhD. So in total, it is of about 6 years, and like 3 years of my MS and 3 years of PhD officially. Okay, so back to our course. Hmm. So one important thing is, like, important link for this course will be, you should mention everyone, HTTP. This is my website. google.com out of mouth. It's small at home, where you will find all my lecture notes, all the relevant things related to this course. I have also pinned this website onto my WhatsApp group discussion. So we shall see things, because this is an introductory class. I shall introduce things to you all. Mm, okay, so my screen is visible to you, right? So you can go to my teaching section. This is my website, and we will be following this particular curriculum I have sent you previously. Okay, is it visible to you all? Hello, is it visible to you all? Sorry, was I mute for how long?
After you opened your website, you're on mute.
Oh, sorry. So this will be the curriculum we will be following. You are seeing this, okay, on screen, I suppose. So course module in our first month we will study the introduction and electromagnetic radiation, Lorentz transformation, space time. In this will be our goal. In the introduction, concepts of relativity, Newtonian physics, Galilean relativity, and then we will jump to electromagnetism, a bit of it. And this course is actually taken through I mean, the MIT course by Scott A. Hughes. Okay, and on top of it, I will refer to notes by Javier Review and the other books as mentioned. So these are the links you will be following throughout the course. Fine. So let's start our main topic. So okay. Mm, yeah. Mm. So also in that website, in the teaching section, you will find my first offline class where I gave some bit of introduction to the history of relativity. You should all read at least one time that. Okay. Now we are actually beginning with what we will do. We will begin with Newtonian relativity, Newtonian or say Galilean in sense. Sorry, my spelling is. Can you remind me the spelling exact? I am confused between this double L or L. Galilean, I suppose it is like that. Okay. So then when we'll upgrade it to Einstein's special theory of relativity, or simply special relativity. Then we will further update into Einstein's general relativity. Okay, so see that in a particular limit, that is uh, Newtonian or Galilean relativity is a special case of this Einstein's special relativity, and the particular limit is called the slow motion limit. Okay, and similarly, this one, the Einstein's special theory of relativity, is a special case of Einstein's general theory of relativity. That's why the name is, and the limit is called weak field limit. I mean, in this limit, the general relativity will start to turn into the special theory of relativity. Or say, we can also say locally, locality is the limit. Locally, the general theory of relativity will be converted into special theory of relativity. Okay, so this is the thing. And also, if we talk about Newtonian gravity, okay, so this is a particular in the particular limit to GR, and that limit is both, that is weak field limit plus the slow motion limit. Okay, in this limit we will get the R Newtonian gravity. Okay, fine. Let's make a table and differentiate between both spatial and general relativity, and with some points. Okay, so let's make some table out here. Okay, okay, fine. So, spatial theory or simply spatial relativity. Okay, and here is my general relativity. Keep writing things with along with me. Okay, it will be better for you. So, first thing it is, in spatial relativity we work in flat spacetime, and in general relativity we work in curved spacetime. We will see how this notion of flatness and curvedness will arise, and how can it be quantified by some mathematical quantity. Second thing is global. We can define inertial frames globally in spatial theory of relativity. But in general theory of relativity, only local inertial frames do exist. Means you can define inertial frames, which we will define in soon, but locally, only locally. You can define your inertial frames only locally in general theory of relativity. Third point is it uses Minkowski. It is a name of a scientist. Uh, It is Minkowski metric, and we denote it by a tensor. This is tensor. These are subscript indices. We will see that what are tensors and all. And general theory of relativity uses sorry dynamical metric, which is a general metric. In general sense, it is a general metric and we denote it by G median. Okay, and it can be a dynamical and it is not dynamical. Dynamical means time dependent or yeah. So fourth point is in spatial theory of relativity, the fundamental thing is Lorentz invariance. It follows a Lorentz symmetry. Okay, but in general theory of relativity, it follows general covariance. We will see what is the difference between invariance and covariance. The fifth point is like in spatial theory of relativity, there is no gravity. We do not explain anything about gravity or we do not take gravity into account. But in general theory of relativity, we will see that gravity will be manifested as the curvature in space-time geometry. Okay, next, uh, last but not the least, is the it has straight world lines. Okay, and in general theory of relativity, we call these such lines as geodesics in curved spacetime. You just write it down now. I will explain everything in detail. Okay, so okay, right, got. Hmm. One important point is that SR is a spatial limit of GR. Okay, such that my G mean will translate to eta. This is eta. Okay. Uh, Let me write it again. Oh, my writing is very practice. Okay, fine. But the condition only applies locally. Okay. Yeah. Now we will define something. Uh, some definitions. Definitions. And first definition is event. Okay, what is an event? It is something. It is something. Okay, that happens somewhere at some time, or precisely, if we call it, it is a point. It is a point. An event is a point in both space and time. Okay, it is a point in both space and time. And a key feature is that it is independent of how we label it. Okay, and the labeling depends, and this labeling depends on our our choice of reference frame. And what is this reference frame? Huh? What is this reference frame? Let's define it then. Okay, what is this reference frame? It is a system. Don't worry about my writing. I will just give you my notes, proper LaTeX notes. It is a system for labeling events in space-time, in space and time. Okay, or it can be, you can say you should have a clock plus a set of coordinates. Okay, plus a set of coordinate or coordinate axis. Okay, tied to a particular observer. Fine. If you have any, one thing I forgot to mention, that we can denote an event by the E as, uh, we can, how should I write this? And we can denote event as E such that with coordinates x, y, and all these coordinates. There should be a time, an x coordinate, and a y coordinate, and a z coordinates. Means you have three spatial coordinates and one temporal coordinate. If you specify these coordinates, then you call it an event. This is a point in both space and time. Okay, and this is just a representation in one reference frame. Okay, it the particular event is actually independent of how we label it. It is like E can be denoted as in one frame as like this at t0. Okay, or it is same in prime frame. Suppose I have a prime frame, it can be denoted as like this. Okay, so let me select it. This can be one, this cannot be shoot. Yeah, this can shoot. Hmm, okay, let us yeah, fine. So now you understood what is a reference frame, right? It is a system for labeling events in space and time both, and it requires a clock and a set of coordinates in axis tied to any observer. Okay, so you may define any event like visiting the your classroom. You need a specific time, and plus you need to mention the place where you need to um, uh, organize any event. Okay, so you need both of these to specify. You cannot like separate. You cannot just to like organize any event. You cannot just uh, use the spatial coordinates to define, or you cannot just say that come to LHC office. Okay, come to LHC classroom. You have to define the time also. So you intrinsically include the time coordinate to define any event, and that's why we are including all these set in a reference frame. Okay, so a reference frame can be of two types. A reference frame can be of two types. That is right-handed coordinate systems in coordinates with coordinate system defined by coordinate system, right-handed coordinate system with right-handed. Let me write the full form of it. Right-handed coordinate system and left-handed coordinate system. Fine. And can any one of you tell me that what is the difference? You have studied it. What is the basic difference between right-handed and left-handed coordinate system? Are you able to listen me?
Yes.
So, can you, anyone, what is the basic difference between right-handed coordinate system and a left coordinate-handed coordinate system? Ever studied these kind of concepts?
No, sir.
We have defined something. Suppose this is your room. Okay, okay, and here you are standing here. Fine, and like suppose this is yeah. You have a wall clock here. You must have a wall clock. Okay, because to represent a time coordinate, and you must specify your coordinate systems, coordinate axis also. So there can be two ways. Suppose this is my, you define this length of your room as x-axis. You define the height of this room as z-axis, and you can define uh, this as y-axis. Okay, so here you have defined all the coordinates, three coordinates t, x, y, and z. Okay, now you can choose this like I will represent this by two ways. I should rather use proper lines instead. Okay, wait. Mhm. Yeah, okay, fine. Yeah, oh, maybe that fine. Yeah. Again, I can represent this one separately. Okay, hmm, fine. Let me write this. Okay, these are my. No. Suppose this is my x, this is my z, this is my x, this is my z, this is my y. Okay, this is my y. And the similar diagram will be shown, can be shown as by this. This is my circle, a circle, okay, and we represent a dot here, okay. And again, you write, you draw a circle and make a cross here on the origin, okay. This is x, this is z, this is y, This is also y. So what is the difference between these two reference system is there you have defined this system when you this is yeah, left-handed coordinate systems and this is right-handed coordinate system. Okay, yeah. So how do you define it? You can curl your fingers. You can like curl your fingers from X to Y with your left hands. Okay, and similarly, you can curl your fingers onto this axis from X to Y with your right hand. So this is the basic difference, and both can be used as the coordinate system, and this can be represented as this, where this signature means pointing out of the screen. Okay, this is screen, and this represents pointing into the screen, pointing in screen. Okay, so this axis is like you are the axis is coming out of the screen, and this shows that the axis y-axis is going into the screen at the backside of your screen. Okay, so we will be using in this course our convention will be we will be using left-handed left-handed coordinate system. Okay, fine. This is our convention for this course. You may find different conventions, okay, left-handed ones in this course. Now we will define another third definition is the geometric object. What is a geometric object? Okay, so a geometric object is something with properties okay that exist independent of the reference frame or the choice of reference frame that we use to describe it or label it. Describe it. Okay. For example, the event E. As we have seen, these were different representations. Yeah, here we have seen that we can describe any event with different reference frames. Suppose in S prime frame there is an S prime frame. It is described by these coordinates, and in S frame and as a reference frame it is described by these coordinates. Okay, so it is an invariant or say independent an event is an independent some quantity which do not depends on actually representations, or we can have different representations of same geometrical object. So this is my first example. Okay, and the second example is like vector. Suppose I have a vector v. Okay, we have studied. This is my first example. This is my second example, and there can be more. So Suppose I have a geometric object. Let me remove the ruler now for once. Okay. Now suppose I have a geometric object. So, I need more weight. Yeah. Okay. Yeah. Fine. Let me select it. Will it be selected? Yes. Okay. Yeah. Let me move it here. I have geometric object. Yeah. This is a vector. What happened? Yeah. P. Okay. It is a geometric object, and we usually define it by a magnitude with some unit vector. Okay. Now see, there I will draw three reference frames. Okay. I will quickly draw three reference frames. Uh, I can define it in either way. So let's draw it more so you can understand it better. Let's define it like this: x, z, and this is y. Okay, you will see that this is a left-handed coordinate system, and similarly, I can draw it like this. Okay, where my y is pointing out of the screen. Okay, and this is x. Similarly, I can draw a reference frame like this. Mm, it is y is again pointing out of the screen. Okay, axis y is pointing out of the screen. Remember that. And my z and x are on the screen. So I can actually draw it better like this if you want. This was just to explain you the x-axis. This is my y-axis. Okay, and this is also my y-axis. Okay, and we can call the origin as O everywhere. Okay, now suppose there is some man here, there is another man like standing like here, this. Okay, oh sorry, I have done a mistake. This is not left-handed coordinate system. Now this is fine. Yes, this is fine. And in this frame, this is again I have mistakenly drawn like this. Uh, this z is actually parallel to the vector. Okay, this z is actually parallel to the vector. Now I have to draw perpendicular to it a z axis. Now this is fine. So in this frame, I have another man who has defined height as the z-axis. Okay, height as the z-axis. You can see in every frame. Okay, and it is standing on the x-axis. Okay, I'm a good drawing. I'm a good sketcher, but this writing pad, yeah. So fine. So in this, we can define our the vector, the direction of this vector. This is a geometric object. We can define this unit direction as Ex. It is a unit vector in the x direction plus unit vector in the z direction. Can you check it is correct or not? Okay, this is my first representation. The second representation is, what will it be? Tell me, how will the this vector look in this frame? How will this person define this geometric object? This person has defined this geometric object based on these coordinates axis. He has like in the x-axis, if he defines a unit vector, eh, you go in this direction plus you go in this direction and you will define the unit vector of this uh, geometric object, that is our vector v. You define the direction by this. Okay, you go into x-axis in x direction, then you go upwards in z direction. Now what will be the direction of v in this frame? Tell me fast. What should I write? It is simple.
X minus eta z square root 2.
Ex minus z root 2. Fine. And this one, what about this one?
Eta z.
It's simply Ez. Yes. So we have defined different representations of a particular geometric object. What we have defined? We have explicitly seen different representations of a geometric object, that is a vector, a particular vector. And it can be a tensor, it can be a scalar, it can be something, okay, that can have different representations. Now I have just a question for you. Okay, okay, wait. Before the question, I should write this, that this vector is equals to v1 modulus, that is the magnitude of this vector, and this representation should be equal to the magnitude into its direction should be equal to the magnitude, sorry. Okay, now the question is, if my v3 magnitude is suppose of 3 units, okay, what will be v1 and v2? Okay, you can find it. Okay, it's easy. Let's move ahead. So thing is that geometric tools are excellent tools. Geometric objects are excellent tools for describing physics, like events, vectors, or tensors, etc. Okay, what are these geometric objects? What are these geometric objects I have defined above? Do you remember what is a geometric object? Tell me first. Remember that a geometric object is independent of the representations. Okay, it is independent of a reference frames we have defined. Okay, it exists independently. We will use such geometric objects and the ways to represent it to describe our universe most fundamental equations of special theory of relativity, or say the normal Galilean relativity. Okay, we describe these with particular reference frame representation. We describe these kind of geometric objects, these kind of geometric objects, okay, with a particular reference frames representation. Fine. Yeah. Let me. Yeah. So let's talk about something else. Let's define what are inertial frames we were talking about previously. Here, that in spatial relativity you can define inertial frames globally, but in general relativity we do only define inertial frames locally. Okay, but what are inertial frames actually? Let's define it. Yeah, wait. Okay, so inertial frames, or the inertial frame of reference. Okay, it is a frame with, sorry, with no external forces or no forces applying on it or acting on it. Okay, such frames do travel with respect to each other, with respect to each other with constant velocity. Okay, so suppose I have a frame here. Okay, this is my xz and this is my y axis. This is my, I call it S frame. I call it S frame. And this is my another frame here. This is prime, Z prime. This was my Y prime, Y and origin defined. This is my Y prime. Okay, and so I will call it S prime frame. And these both reference frames will move with a constant velocity with respect to each other. If you are here, suppose if you are here, okay, you are here, you will see this frame going away in this x direction, S prime frame in this x direction with respect to S frame, okay, with a constant velocity v, with a constant with velocity which is constant, constant velocity v. Okay, in this particular direction, positive x direction. But with respect to s prime frame, what will happen? You will see the frame, s frame, going in this negative x direction. Okay, with constant velocity. With constant velocity, oh sorry, you may not be able to see this in the recording here. So in s prime frame, sorry, in s frame, with respect to s frame, you will see the s prime frame. mm, uh, with respect, I have written something else. Sorry. With respect to s frame, yes, the s prime frame is going this words, and when you stand on the s prime frame, yeah, then the s frame will go in this negative x direction with a constant velocity, that is v, that is negative v, negative of v. Okay, this is positive of v. So it depends on what reference frame you are choosing to observe things. Okay, if you are standing here on the s frame, you will see the s prime frame moving with a positive velocity, means moving in the x positive x direction. And if you are standing on this particular s prime frame, you will see this s prime as at rest, but this s frame moving with a opposite velocity. This can be observed easily in the scenarios when you travel with in the vehicles, or suppose train. Okay, so inertial frames are actually unaccelerated frames. Okay, so inertial frames, what are inertial frames? Are unaccelerated. They should not accelerate somehow. Why? Because no force is acting on it. For example, gravity. Unaccelerated frames. Now, uh, we are going to stop this class in 5 minutes. But what about non-inertial frames? What are these? Just opposite of these frames. Non-inertial frames are accelerated frames. Okay. In such frames, in such frames, we usually introduce. What do we introduce in such frames? Can anyone guess what we call?
Pseudo force.
Yeah, what we call fictitious or pseudo forces. We usually we usually forces. Okay, but there is nothing. Okay, for example, centrifugal force, or say the Coriolis force. Have you ever studied this kind of force? Yeah, centrifugal. You know. Do you know the Coriolis force?
Yes, sir. Yes.
Yeah, you have studied in the mechanics course, I guess. Now, there is nothing fictitious about these forces. Like in one frame, forces may seem like fictitious, actually fictitious. That how is this force arising in a particular frame? But in another frame, it may not be fictitious, may not be fictitious, but actually it is not fictitious. This implies it is not fictitious. If you can define fictitious force in other frames, then means it is not fictitious. Of course, it is applying on you. It is real, physical. Okay. If you are riding a bike, suppose, okay, whatever it is, on a curved road and you feel a centrifugal force and you fall here and you will get hurt, you will say it is actually not fictitious because you have felt the pain, because you have felt it physically. So something is happening, something is real. So if you change the frames, we will talk about these things in later in the course. So there is nothing fictitious about fictitious forces. They are real, but in one frame they may seem fictitious, but they are real physical forces. Okay. So we will end this class here. End this class here. And in the next class, we will use this. We will see how to relate, actually, how to relate quantities, okay, as described in one frame reference, in the one reference frame to another. Okay, and how will how we will see this? It is we will see this by relating the representations, the different representations of geometric objects. Okay, by studying or relating the different representations of the geometric objects, and the geometric object can be anything like vectors, scalars, or tensors, or like events, and those geometric objects are actually independent of the representation of the reference frame, choice of reference frame. So that's all for now, and it will be interesting that these, when we will study these in general sense, okay, in general sense, to any moving, any uh, object moving, okay, moving slowly. Here we will define the slow limit. The slow limit is the v very, very, very smaller than the speed of light. That is our usual speeds we experience in daily life. Okay. Usual speeds, these are usual speeds we experience in our daily life. Even the speed of rocket or spaceships, normal spaceships, okay, are very, 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 very less than speed of light. Okay, so in this limit, in this slow limit, we will see in this slow limit the physics of constantly, not constantly, of moving objects here. We can study accelerations in spatial theory of relativity, but not the accelerated frames of reference. Okay, note that. Note this. This is the final thing in spatial theory of relativity, or say in SR, frames, sorry, objects can accelerate, but frames do not. We will see further the generalizations, but for now in SR we will see this, and we will further see that it is governed by some symmetry. Okay, some symmetry which is called Lorentz symmetry. Whole SR, whole special theory of relativity, is governed by Lorentz symmetry. It is again a name of a scientist, Lorentz. Okay, so wherever there is a symmetry, there are conserved things, there are conserved laws. We will see that. So for now, this is enough today for now. So if you have any questions, you can tell me or ask me. So what did you learn today? Basically, I'm just putting off my screen, turning off my screen now. So this was all about constantly moving frames. Okay, so if the reference frames are moving constantly, then we will see how the physics will look in those frames. How can we translate physics from one reference frames to the other reference frames? Okay, and we will see that while translating these things in the low speed, how will the transformation equations will look like. But if we suppose increase the speed to approximately the speed of light or up to the speed of light, what will happen to the system? And we will see, actually the Albert Einstein have concluded this, that we will see various kind of interesting phenomena, like time dilation, that uh, which is like moving clocks do run slower. Okay, uh, and also the length contractions. Okay, moving lengths do get contracted. Okay, as the velocity of the moving objects approaches near to the speed of light, many weird things start to happen, and we will see in the course later on this course that what are the governing equations of that, and we will see more interesting phenomena arising from those equations. Okay, like simultaneity and all. There are many interesting topics in special theory of relativity. So this was a formal introduction. Okay, so let's meet tomorrow morning again.